Okay, so we've done 2 examples of exponential growth. Now we're going to do an example of exponential decay, and we're going to do that in terms of, and we're going to do an example involving radioactivity in a sample of stuff. All right, so we're introducing here the concept of half-life. Half-life is the amount of time it takes for half the original amount to decay. All right, so in this case, this isotope has a half-life of 1,620 years. The original amount is 5 grams. How much would remain after 10,000 years? So here's what we know. We know that our model is y equals AE to the BT, and we know that B is going to be negative. We do not know what B is, but what we do know is that after 1,600 years, we only have half the original amount. The original amount was 5, so in 1,620 years, we're going to have 2.5 grams. So 2.5 equals 5 e to the 1620 b. So now I'm going to divide both sides by the 5. That's giving me 1/2 equals e to the 1620 b. Take the natural log of both sides. Ln of 1/2 equals 1620 b, so that b equals ln of 1/2 over 1620. And this is always going to be true, by the way. The decay constant, because that's what we'll call b, is always going to be the ln of 1/2 over the half-life. So that's a little shortcut that you can use. Now that we know the decay constant, we're going to store it in our calculator. Store as b. So ln 1 over 2 close divided by 1620 store alpha b. All right, and notice that this is a negative number and that it's very, very, very small because this is decaying very, very slowly. All right, and it's a good thing we had that stored because I don't want to type it in. So now we want to know how much would remain after 10,000 years. Same equation. Y equals, we know that the initial amount is 5, e to the 10,000 b, and I'm using a capital B here because I have that value stored in my calculator. So all I need to do is type this in. Five E to the 10,000 alpha b. 0.0693. After 10,000 years, there will be 0.0693 grams of the isotope remaining. All right, now we are not going to bother addressing the Gaussian model, though any of you that are in statistics might be interested in taking a look at some of those examples. I'm not concerned with them. We are going to, however, consider the logistic model. Logistic model is one that has a cap. All right? Unlike exponential growth, we're going to grow very fast for a little while. Then we're going to slow down as we reach our constraint. So, here's our example. On a college campus of 5,000 students, one student returns from vacation with a contagious flu virus, and the spread of the virus is modeled by this equation. Notice, the top number is 5,000. That is our constraint. And that makes sense. If there are only 5,000 students on the campus, then there cannot possibly be more than 5,000 students infected. All right? The college will cancel classes after 40% or more of the students are infected. So first, we want to find out how many students are infected after 5 days. Well, this is a straight up calculator problem. All right, plug in 5 for t. 5,000 divided by, open, 1 plus 4999 second e to the negative 0.8 times 5. Get out of it, close your parentheses, and enter. 54. After 5 days, we have 54 students that are infected. All right? Second part. After how many days will the college cancel classes? All right, so we want to look at this equation right here. And we want to know, after how many days is the college going to cancel classes? Well, we know that the college cancels classes when 40% of the students are sick. 40% would be 2,000. So if there are 2,000 kids sick, then they're going to cancel classes. So, we have 2,000 equals 5,000 over 1 plus 4999 e to the negative 0.8 t. All right, and we are going to, what I'm going to do is I'm going to multiply both sides by the denominator. But rather than divide and distributing that 2,000, I'm going to divide both sides by 2,000 as well. So I'm going to multiply by 1 plus 4999 e to the negative 0.8 t. Same thing on this side. And then I'm going to divide everything by a 2,000. Gone, gone. This gives us 1 plus 4999 e to the negative 0.8 t equals 5 over 2, which is 2.5. Okay? So, now I am going to subtract the 1 from this side. That gives me 4999 e to the negative 0.8 t equals 1.5. Then I'm going to divide both sides by 4999. E to the negative 0.8 t equals 1.5 over 4999. I know that to undo the e, I have to take the natural log. Negative 0.8t equals the natural log of 1.5 over 49.99. And then last but not least, I'm going to divide everything by negative 0.8. So I have t equals natural log of 1.5 over 49.99, all divided by negative 0.8. I put this in the calculator. Natural log 1.5 divided by 4999 close divided by negative 0.8. That gives me 10 days. So notice, we went over the course of 5 days from having only 54 students infected to having 40% of the student population, 2,000 people infected. Let's look at this graph. Okay, look at our graph. This is graphed over the time interval of 0 to 25 days. So notice at first, the number of infections is increasing very, very slowly. And then after a little while, it shoots up really, really fast until it gets to the point where you have almost everyone or everyone on the campus infected with the flu. So that's a logistic model. Exponential growth, exponential decay, and logistic models are the ones that we are the most likely to be addressing in this class because they are the ones that happen the most frequently in nature.